Pendulum. A small rock with mass 0.12 kilograms is fastened to a massless string with length 0.8 meters to form a pendulum. The pendulum is swinging so as to make a maximum angle of 45 degrees with the vertical. Air resistance is negligible. Part A. What is the speed of the rock when the string passes through the vertical position? What is the tension in the string in part B when it makes an angle of 45 degrees with the vertical? In part C, as it passes through the vertical. So you can see here we have a pendulum, length L, a mass M is attached to it. It's a massless string. So if this string makes an angle theta degrees with respect to the horizontal, you can see that the mass M has traveled a distance delta H upwards, and the distance between the contact point to the ceiling and the horizontal level will be H. So from this geometry, it's mentioned in the problem that the maximum value of theta is 45 degrees. And this length L of the string is 0.80 meters. And when the mass goes up a distance delta H, this delta H will be equal to the length of the string minus H, which is L minus L cosine theta. So you can see that this is L sine theta, this is L cosine theta. So L minus L cosine theta is the distance we travel in the vertically upward direction. So part A. So first of all, I want to note that the speed of this mass, the speed v, is going to be a function of the angle theta. So it's a function of angle theta, which is the angle we make with respect to the vertical axis. So this angle is with the vertical axis. And how does that behave? Such that we're going to have, in the maximum possible angle, theta maximum, the speed will be 0 meters per second. All of the kinetic energy will be lost. So if I define the potential energy of the system at theta is equal to 0 as 0 joules, then when I reach an angle theta, I'm going to have a potential energy mg delta H. As you can see here, the potential energy at this point is 0, and the potential energy at this point is mg delta H, which is equal to mg times L minus H, which is mg L minus L cosine theta. Now the kinetic energy at the maximum angle, theta maximum, will be 0. And when I write the change in the mechanical energy of the system, delta K plus delta U, this should be equal to 0. Why? Because there is no air friction, no friction in the system, so mechanical energy must be conserved. Then what is the kinetic energy at theta equals to 0? So the kinetic energy at the maximum angle, theta maximum, minus the kinetic energy at theta is equal to 0, plus the potential energy at theta maximum minus potential energy at theta is equal to 0 is going to be equal to 0. The kinetic energy is 0 at the maximum angle, minus 1/2 m. I want to know the speed when theta is equal to 0. So this will be squared. This is going to be added to the potential energy mgl 1 minus cosine theta maximum. Potential energy at theta equals to 0 is 0. So I have taken this into L parentheses, so mgl 1 minus cosine theta maximum. So if I isolate the speed, 1/2 m, the speed at theta equals to 0 squared must be equal to mgl 1 minus cosine theta maximum. M's will cancel, and I will be left with the speed at theta equals to 0 given by 2gl 1 minus cosine theta maximum square root. So when we plug in the numbers here, this will be 9.8 meters per second square, length is 0.8, 1 minus cosine 45 degrees square root, and the answer is 2.1 meters per second. Okay, so the question was, what is the speed of the rock when the string passes through the vertical position? That is, theta is equal to 0, so I find the speed to be 2.1 meters per second. Now moving on to part B. In part B, I want to know the tension. Okay, so what I want to do is draw a free body diagram at theta is equal to 45 degrees. All right, so the tension makes an angle of 45 degrees with respect to the vertical axis, and there is the weight of the block pointing down, that is mg. So that also makes an angle 45 degrees with respect to the radial axis. So this is our radial axis, r hat. As you can see, we're moving on a circular path here. So this is a circular path. We're moving on this arc. So if I write the net force in the radially outward direction, it would be mg cosine 45 minus tension, which is equal to mv square over r, mv square over L. Or if you wish, the centripetal force here is tension, so the center is here. The tension minus mg cosine 45 is minus mv square over r hat, so that's the same equation. And this gives us, for the tension, mg cosine 45 why? Because at this point, at the maximum angle, the speed is 0. So v theta max is equal to 0. So this gives us the tension 0.12 times 9.8 times square root 2 over 2. The tension is 0.83 newtons at this point. Part C asks me the tension when I reach the vertical position. So if I draw the free body diagram at theta is equal to 0 degrees, I will see that there is the new value of the tension pointing up and there's the weight pointing down. So here is mg, here is tension T prime pointing up. Now the radially outward direction is pointing down. So we are at the bottom of this circular arc here. So this is the radially outward direction. The net radial force will be mg minus T prime which is equal to mv squared over r, where r is the length of the string. So I find that the tension at this point should be equal to mg plus v squared divided by L. So if I substitute the numbers here, 0.12 kilograms times 9.8 meters per second square plus v square at theta is equal to 0. So v square at theta is equal to 0 is here 2gl1 minus cosine theta max. So it is 2gl1 minus cosine 45 degrees. This should be divided by L, which is 0.8. So the L's will cancel. And this gives me a numerical value of 1.9 newtons for the tension at the vertical position. Okay, so in this problem we're talking about a simple pendulum. A rock with mass m is attached to a massless string with length L, and there's a maximum angle that this string will make with respect to the vertical axis. We want to know the speed of the rock when it passes through the vertical position. We want to know the tension in this position and tension in the maximum angle. So this geometry tells us that when the rock moves a distance delta h with respect to the bottom of its path, it also has a distance L minus L cosine theta with respect to the bottom, because this distance h is L cosine theta, the total is L, so it's L minus L cosine theta is delta h. So I define the potential energy at the bottom to be 0, then I have a potential energy of mg delta h on top. So when I reach the maximum angle, this will be mg L minus L cosine theta maximum. The kinetic energy at the maximum angle is 0. And therefore, using the conservation of mechanical energy, since there is no external force or there is no friction on the system, I can write this equation, and this gives me 0 final kinetic energy minus 1/2 mv squared plus the potential energy in the maximum angle mgl 1 minus cosine theta max minus 0 equals 0. So I can pull out the speed from this equation. And to calculate the tension in the two positions, theta max and theta equals to 0, I draw the free body diagram. And for the theta max case, the tension makes an angle 45 degrees with the vertical, and radially outward direction is also making an angle of 45 degrees with the vertical. Since this is a circular path, I can write the centripetal force to be T minus mg cosine 45 equals minus mv squared over r, but the speed at the maximum angle is 0, so this gives us tension equals mg cosine 45. And in the vertical position, T prime minus mg is the centripetal force, which is equal to minus mv squared over L. And we know the speed at the bottom of the path is square root 2gl1 minus cosine theta max. We substitute for v square, it's square. So we plug in the numbers, and this gives us an increased tension 1.9 newtons. So you can see that the tension is decreasing as we go up, and it's increasing as we go down on this circular path.